Right, so welcome everyone for this last part of classical statistical mechanics. So what we are going to do is discuss the problem of generic versus specific phases, okay? And what we are going to use, that's the reason why I'm going back to this page, is basically this expression, okay? That we can make a correspondence between the partition function, the canonical partition function, and the log of it is basically proportional or identifiable, if you will, to the Helmholtz free energy. Okay, so what we are going to discuss then is this problem of generic versus specific states. So when we have identical particles, that's important here, this is identical particles, then we've seen that there are two possibilities, okay? Imagine two red particles that you see, and they are, one on your left and one on your right, and then you, let's say, close your eyes, and then you open them again. And you don't know whether, for example, somebody has been playing with you and maybe has swapped them, and you don't know whether this is the same state, if you will, as before. So there are two positions one can take about it. One is basically calling them generic states, or in that case, it does not matter whether the particles have been swapped. The only thing you want to know is that there is a red particle on your left hand side and a red particle on your right hand side. Period. You don't care about much more. Now, specific states are states where you want to say, no, the particle number 1 is on my left and particle number 2 is on my right. And if this were to be swapped, then that would be a different state. Okay? And we want to know, when we do statistical mechanics, which ones we ought to use. Or at least we want to justify why. Okay? So the bottom line that we're going to use, so the basic idea, okay, is that sorry, I need to use this. So the idea is to use the correspondence, okay, the thermodynamic correspondence okay, that we have discussed so far, and in some sense and inform our theory of statistical mechanics, so our theory with thermodynamics. Okay, so with some thermodynamics postulates or knowledge, thermodynamics. Okay, so what we are going to do is look at the Helmholtz free energy. Okay, and that's called A. Okay, and the way we are going to write it is that I just remind you that we've seen that beta A was minus the log of Q divided by H to the dn. Okay, and so there are two possibilities, therefore. Okay, so there is the first one, possibilities. So the first one is beta A specific. Okay, so that's minus the log of Q specific, which is, if you will, the normal kind of Q, HDN. And then we've got beta A generic, okay, which would be minus the log of Q specific, so it's still the same kind of integral of a whole phase space that we calculate, but then with n factorial h to the dn. Okay, if you don't remember these things, I encourage you to look at the past lectures. I think it was week 6 lectures where we discussed this 1 over n factorial factor that would arise from generic versus specific partition function. Okay, so now what we are going to do is to say, so to discriminate which one is correct, if you will, so to discriminate which one is correct, okay, we are going to use the extensivity property, extensivity of beta A. Okay, so that's what we want to do. So here, what we have discussed in thermodynamics was mostly for ideal gases, or at least for simple compressible systems. And so what I'm going to do here is basically I have to say here that is going to be applied to a system of n free particles in a box of volume V. Okay, so so what we know in that case is that if we have this, then we know what Q specific is, right? This is something we have calculated multiple times. So Q specific in that case would be equal to V to the n, and then 2 pi m over beta, and then 3n over 2. All right? So then what I can do then is, therefore, beta A specific is equal to minus, and I directly kind of, decompose use the properties of the log. So minus n log V, and then minus 3n over 2 log of, well, basically all these things. So 2 pi m over beta. And that's it. Now I can reformulate it in a different form. It does not really make any difference. But one of the things we can do then is that sorry, I forgot the h. I was about to forget the h. So plus 3n log of h. Okay. So what we can do then is look at beta of A specific, where I've got lambda n and lambda v. And beta is, I remind you, 1 over kBt. So this is an intensive variable. So what we'll get is minus lambda n log of lambda v, and then minus 3 lambda n over 2 log of 2 pi m over beta, and then plus 3n log of h. Okay, so what we see here is that there is kind of a problem. So I can decompose it in the following way. That would be lambda. Okay, so let's do like this. So lambda n log of v. Okay, then minus 3 lambda n over 2 log of 2 pi m over beta plus 3n log of h. And then there is an extra term here, which is minus lambda n log of lambda. Okay, so all in all, this is equal to beta A specific of n, v, and beta, but then minus lambda n log of lambda. Okay, so what is sure from this is that this is not extensive. Okay, if you don't remember what extensive means, then again I encourage you to have so that's lambda times beta A. So what this means is that beta A of lambda n lambda v should be equal to lambda A of nv. Okay, and because this is not the case, as there is this extra term here, then the specific partition function kind of doesn't do the job. Now what we want to check is what about the generic one. So the generic one would be the same, okay? So now we can do beta generic, beta A generic, okay? And I can directly do lambda, no, I can't do lambda n, let's do step by step a little bit. So that would be n v beta. And then in that case, that's almost the same as before. Okay, so what I will do, I will simply say this is beta A specific, okay, of n v beta. But then there is minus log of n factorial. Alright, so, and in fact it's not a minus, it's a plus, because it's q over n factorial, okay, so that's it. So if you take minus log of q, that's plus log of n factorial. And then what I'm going to do is express this in the following manner by using Stirling approximation. So specific nv beta, and then plus n log n minus n. Okay, so that's, here I've been using Stirling approximation. So that's if n is large enough. Okay, and then it's simple because I can simply do beta A generic and then lambda n lambda v beta. So that would be approximately, and I know that from before, so that would be lambda beta A specific. Okay. Then I've got this extra term minus lambda n log of lambda, and then I've got plus lambda n log of lambda plus lambda n log of n, and then minus lambda n. So what we see here is that this lambda n, so this term here, will cancel with this one, okay? And so these guys cancel out, and all in all we get the following expression, so that approximately equal to lambda times beta A specific, okay, and then plus n log n minus n, okay, which is lambda beta A generic. And then this is extensive. Okay, so what we see here is that if we take this prescription of looking at generic phases, then this Helmholtz free energy is extensive. So that's what I want to say here. To retrieve thermodynamics and the extensive character of A, but also that would be anything else, so S, U, anything else like this, right? What we want to say is that generic phases must be used. So here this is really, really important. Must be used for systems with identical particles. So if you are told in a question from now on, if you are told in a question that you are having identical particles, and here maybe I should say in classical statistical mechanics, okay. The same will hold as well in the quantum part, but somehow that comes not more naturally, but that comes for kind of for the same reasons. Okay, so that's basically the end of the classical statistical mechanics part, and that we finish by basically almost putting the final nail in the framework where we can link statistical mechanics with thermodynamics and essentially closing the loop with the very first week lectures that we have given. Okay, and so what we are going to do in the coming lectures and short lectures that will come will be looking at how do we change the formalism of statistical mechanics once we want to make it quantum mechanical. Okay, so then see you next time.